Welcome to video number 11 for Physics 102. This video is on the distinction between conservative forces and non-conservative forces. By the end of this video, you should know how to determine if a force is conservative or non-conservative, know which types of forces are associated with potential energies, conservative forces or non-conservative forces, and know how to incorporate non-conservative forces into problems using conservation of energy. Let's begin by considering a ball near the surface of the Earth. The ball begins 3 meters above the ground, falls, and bounces back up to its original height. How much work is done by gravity in this case? Well, work is always defined as the force of interest times the displacement times the cosine of the angle between the force and the displacement. In this case, the force we're interested in is gravity, mg. So the work done is mgd cosine theta. On the way down, the force is parallel to the displacement. The ball is moving down, and the force is down. So the angle between the force and the displacement is 0 degrees. The cosine of 0 degrees is positive 1. So the work done by gravity as the ball travels down is positive mgd. On the way up, however, the force is down and the displacement is up. So the force and the displacement are anti-parallel, or the angle between them is 180 degrees. Now the cosine of 180 degrees is negative 1. And so the work done by gravity as the ball travels back up is negative mgd. The total work done by gravity on the entire loop is the sum of the work done by gravity on the way down plus the work done by gravity on the way back up, which in this particular case is equal to 0. The ball in this particular example is moving on what is called a closed path. The ball starts and stops in the same place. We've just seen that for this particular closed path, the work done by the gravitational force is equal to 0. It turns out that the work done by gravity on any closed path is equal to 0. This leads to a question. Is this statement true for all forces? Is the work done by any force on any closed path always equal to 0? To answer this question, let's think about a different force, friction. In this example, we have a 2 kilogram box as it's dragged 3 meters across a table with a coefficient of kinetic friction of 0.2 and back. And we're interested in the work done by the force of kinetic friction over this closed path. Once again, the work, as always, is the force times the displacement times the cosine of the angle in between. In this case, the force of interest is the force of kinetic friction, which we know to write as the coefficient of kinetic friction, uk, times the normal force. The box is not moving in the vertical direction, which I've called y in this example. So we know that the acceleration in the y direction is equal to 0. Thus, by Newton's second law, we know that the force in the y direction is equal to 0. The net force is equal to 0. Thus, we are able to conclude that the normal force in this particular problem is equal to the weight of the box, mg. Thus, we have the force of kinetic friction, uk times mg. As the box is dragged to the left, the force of friction is opposite the displacement. Thus, the angle between them is 180 degrees. The box is moving to the left, but the force is opposing the motion. The angle between them is 180 degrees. The cosine of 180 degrees is, once again, negative 1. And so the work done by the force of friction as it moves to the left is minus μk mgd. On the way to the right, the force is still opposite the displacement. Now the box is going to the right, but the friction is still opposing the motion. So the angle between the force and the displacement is still 180 degrees. Which means that the work done by friction as the block goes to the right is also negative μk times mgd. Thus we see in this case that the work done by the force of friction around this closed path, the box starts and stops in the same place, so this is a closed path, the work done on this closed path is minus 2 μk mgd, which is not equal to 0. Thus it seems that we have two different types of forces. We have forces for which the work done over a closed path is always equal to zero. An example of this is gravity. We call such forces conservative. We have another type of force for which the work done over a closed path is not equal to zero. The frictional force that we just saw is an example of this. Forces for which the work done over a closed path is not equal to zero are called non-conservative forces. The definition of a conservative force is a force for which the work done by the force over a closed path is equal to zero. So this is the statement you can use to determine if a force is conservative or non-conservative. Why do we care about this distinction between conservative and non-conservative forces? Because only conservative forces are associated with a potential energy. To explore this idea, let's consider a block sliding down a frictionless ramp and a block just falling to the ground. Both of these blocks travel the same vertical distance, h. In both cases, the work done by gravity is equal to the change in gravitational potential energy. The work done by gravity is written mathematically as a negative delta U, or negative delta of mgh. The reason we can write the work done by gravity in terms of a potential energy is because gravity is a conservative force. Friction is not a conservative force. Thus, we cannot write the work done by friction as the change in some type of frictional potential energy. So, how do we include non-conservative forces in our energy calculations? Well, let's return to the block sliding down the ramp. If there's no friction, we know how to proceed. We have the initial potential energy, the initial kinetic energy, equal to the final potential energy plus the final kinetic energy. If the block begins from rest, then the initial kinetic energy is equal to zero. I'm going to define the gravitational potential energy at the bottom of the ramp to be equal to zero, so that the final potential energy is also zero. And so we have that the initial potential energy is equal to the final kinetic energy, with this choice of potential energy 0 at the bottom of the ramp. What if we wanted to add friction to the ramp? Well, the way we would do this is by adding the work done by the non-conservative friction force to the left-hand side of our energy conservation equation. Let's see how this works. We still have the initial kinetic energy and final potential energy equal to 0. I haven't changed anything there. But now we have a frictional force. The work done by friction is negative. Since the initial potential energy is the same, the final kinetic energy of the box is going to be smaller at the bottom of the hill than in the frictionless case, which matches our everyday experiences. So let's summarize. We've seen that there are two classes of forces. Forces over which the work done over a closed path is 0, such as gravity. Such forces are known as conservative. And for these types of forces, we can describe the work done by the force as a change in the potential energy. Work equals minus delta U. We also have forces for which the work done over a closed path is not equal to 0, such as friction. For these non-conservative forces, we cannot describe the work as in terms of a change in potential energy. There is no such thing as a potential energy for friction. If we want to include non-conservative forces into our energy calculations, we have to add the work done by the non-conservative force to the left-hand side of our energy conservation equation. This concludes this video.